Have you ever wondered why you can feel the sun's warmth on a bright day but the space it shines through is freezing cold? It's a fantastic question that takes us on a journey across 93 million miles. Let's start with our star, the sun. It is a gigantic ball of superhot gas, so enormous that you could fit over 1 million Earths inside it. Its surface blazes at about 10,000 degrees Fahrenheit. Now, you might think the sun is yellow or orange, but if you could see it from space without our atmosphere in the way, it would look bright white. This is because it shines with all the colors of the rainbow mixed together. This incredible star is the source of almost all the energy in our solar system, sending light and warmth out in every direction. So, the sun is like a giant bonfire in the middle of our cosmic neighborhood. But understanding its warmth means we need to think about two different things: heat and temperature. Heat is a type of energy. It's the total energy of all the little moving particles, called atoms, inside an object. Temperature, on the other hand, is a measurement of how fast those atoms are moving or vibrating. If the atoms are moving very quickly, the temperature is high. If they are moving slowly, the temperature is low. The sun has a ton of heat energy because it's massive and full of zipping, buzzing atoms, which is why its temperature is so incredibly high. Now, how does all that energy get from the sun all the way to us here on Earth? It travels through a process called radiation. Imagine the sun is sending out tiny, invisible packets of energy, like little light beams, in all directions. These energy packets are called electromagnetic waves. They can travel through the complete emptiness of space without needing anything to carry them along. This is different from how heat usually travels on Earth. If you touch a hot stove, the heat moves directly into your hand. That's conduction. If you feel the warm air rising from a heater, that's convection. But in space, there's almost nothing for heat to touch or move through. So, space itself doesn't really have a temperature in the way we think about it because it's mostly a vacuum. It's empty. There are hardly any atoms or particles floating around between the planets. Since temperature measures the movement of atoms, and there are so few atoms, there's nothing to measure. That's why the temperature of the vacuum of space is incredibly cold, around -454 degrees Fahrenheit. The sun's energy just passes right through this emptiness without warming it up, like a beam of light shining through a clean window without warming the glass itself. The energy is on a journey, waiting for something to run into. Let's follow one of those energy waves from the sun as it zooms through the solar system. This energy, traveling as radiation, is on a mission. It shoots out from the sun and travels at the speed of light. For millions and millions of miles, it moves through the vast, dark emptiness of space. During this part of its trip, the energy doesn't warm anything up because there is almost nothing there to absorb it. Think of it like throwing a baseball across a huge, empty field. The ball is moving and has energy, but until it hits something, like a catcher's glove, that energy isn't transferred. The space between the pitcher and the catcher doesn't get hit by the ball. The sun's radiation works in the same way. It's a traveler, not a space heater. This is a key reason why space stays so cold. For space to get warm, it would need to be full of particles, like air or dust, that could absorb the sun's energy, start vibrating faster, and then bump into each other to pass that warmth around. But space is a vacuum, which means it's defined by its lack of particles. The few stray atoms that do exist are so far apart that they almost never interact. So, even though incredible amounts of energy are constantly flowing through space, the space itself remains a deep, deep freeze. So what happens when the sun's energy finally hits something? That's when the magic happens. When sunlight strikes an object, like a planet, a moon, or even an astronaut's suit, the atoms in that object absorb the energy. This makes the atoms start to vibrate faster and faster, and the object's temperature goes up. Suddenly, that cold, empty space has a very hot object in it. For example, if you placed a rock in space and pointed it toward the sun, the side facing the sun could get heated to over 250 degrees Fahrenheit. That's hotter than boiling water. It's all about having something solid to catch the energy. But here's the tricky part. Only the side facing the sun gets hot. The side of the rock facing away from the sun is in shadow, and it gets incredibly cold because it's radiating its own heat away into the empty void. It might drop to hundreds of degrees below zero. This is why astronauts wear special suits that are white to reflect the intense sunlight, but also have heating and cooling systems built in. They are dealing with extreme heat and extreme cold at the very same time, all because space is a vacuum that doesn't hold or distribute warmth. So, if objects in direct sunlight get super hot and objects in shadow get super cold, why don't we experience that on Earth? Why don't we roast during the day and freeze solid at night? The answer is our amazing atmosphere. Earth is wrapped in a layer of gases, mostly nitrogen and oxygen, that acts like a cozy blanket. This blanket does several wonderful things for us. When the sun's energy waves arrive at Earth, they don't just hit the ground directly. First, they have to pass through all the layers of air in our atmosphere. The atmosphere helps to scatter the sunlight and distribute it more evenly. This atmospheric blanket is great at trapping heat. During the day, the sun's radiation passes through the air and warms up the land and the oceans. As the ground heats up, it radiates some of that heat back out, but instead of escaping directly into space, a lot of that heat gets caught by the gases in our atmosphere, like carbon dioxide and water vapor. This is called the greenhouse effect, and it's what keeps our planet at a comfortable temperature. It stops our planet from getting too cold overnight, holding onto the day's warmth long after the sun has set. Without our atmosphere, Earth's temperatures would swing wildly, just like on the moon. Our atmosphere also protects us from some of the sun's more harmful radiation. It acts like a giant filter, but it also changes how we see the sun. The reason the sun looks yellow to us is because our atmosphere scatters the blue and violet light more than the red and yellow light. When the sun is high in the sky, we see the remaining yellowish-white light. During a sunrise or sunset, the sunlight has to travel through much more of the atmosphere to reach our eyes, scattering even more of the blue light and leaving behind the beautiful reds and oranges we see. It's all thanks to the particles in our air. So, when you feel the sun's warmth, you're not just feeling the direct radiation. You are also feeling the air around you that has been warmed up by the sun and the ground. The heat is transferred to you through convection, warm air currents, and conduction, like touching the warm ground. This is the big difference between being on Earth and being in space. On Earth we are surrounded by matter that can hold and move heat. In the vacuum of space, you only feel the heat if you are directly in the path of the sun's powerful rays. Our atmosphere is the key to our planet's comfortable climate. Putting it all together, we can see that space isn't cold because the sun is weak. The sun is incredibly powerful. Space is cold because it's mostly empty. The sun's heat is a form of energy called radiation, which travels in straight lines. It needs to hit an object to transfer its energy and create warmth. Without particles to absorb this energy, the vast stretches between stars and planets remain at a temperature just a few degrees above absolute zero, the coldest possible temperature in the universe. It's a place of extreme contrasts, where things can be either scorching hot or unbelievably cold depending on whether they are in the light. Think about the other planets in our solar system. Mercury, the closest planet to the sun, is a perfect example of these extremes. During its long day, temperatures on its surface can soar to about 800 degrees Fahrenheit, hot enough to melt lead. But because Mercury has almost no atmosphere to trap that heat, its nighttime temperatures plummet to a chilling minus 290 degrees Fahrenheit. The planet can't hold on to the sun's warmth, so one side bakes while the other side freezes. This dramatic temperature swing shows exactly what happens when there's no atmospheric blanket to keep things balanced. Even here on Earth, you can experience a tiny version of this effect. On a clear night, the ground loses heat much faster than on a cloudy night. That's because clouds act like a temporary blanket, trapping some of the heat that the Earth is radiating. Without clouds, that heat escapes directly into space, and the temperature drops more quickly. This is why deserts, which often have clear skies, can be very hot during the day but get surprisingly cold as soon as the sun goes down. It's a small-scale demonstration of how important it is to have something to hold on to heat. So, the next time you stand outside and feel the sun's gentle warmth on your face, you can think about the amazing journey that energy took to reach you. It traveled 93 million miles through the freezing, empty vacuum of space, waiting to find something to warm up. And thanks to our planet's special atmosphere, that energy is captured and shared, turning what would be a world of harsh extremes into the comfortable, life-filled home we know and love. Space is cold, not because the sun is far away, but because there's nothing in the emptiness to catch its fiery breath.